It is a section 14.8, method of Lagrange multipliers. Here we have a recall. In section 14.6, we studied this. Given a level curve, f of xy equals k, the gradient vector is normal to the curve and pointing the fastest increasing direction. This claim is also true for level surfaces. The gradient vector is normal to the surface and pointing the fastest increasing direction. In this section, we'll consider such optimization problem. We'll use the Lagrange's method to solve this problem, maximizing f of x and subject to g of x equals c. That is called a constraint. Look at this figure. Z equal f of xy is given here, so that the maximum is happening here. But this constraint means that x must be chosen satisfying this level curve. So we have here a red curve, that is g of x equals c, so that the maximum may happen at this point. Now we consider level curves of this function, then we have such contours, and that is the constraint. Now this is the corresponding point. Then at this point, the gradient of f and gradient of g must be parallel. The reason is the gradient is normal to the curves and pointing the fastest increasing direction. The major thing is the gradient vector is normal to the curve. So from this, level curve is normal. And that is increased direction, so it is given there. And g of xy equals c, again, normal. But this level curve and this constraint are tangent at this point, so that the gradient must be parallel. It can be opposite direction. However, they must be parallel. So we have such conclusion. Gradient of f is parallel to gradient of g at maximum. This observation introduces the method of Lagrange multipliers. We try to find the maximum and minimum values of f of xy subject to g of xy equals c along with this strategy. Now, these two vectors are parallel. It can be written with this equation. Gradient of f is lambda with a constant times gradient of g, and g of xy equals c. It must be there because xy should satisfy this constraint. Now we have, from here, we have two equations and one more equation. So there are three equations. What we have to do is to determine x, y, and lambda, three variables and three equations, so we can solve the problem reasonably. It doesn't mean it has unique solution because it's non-linear. It can be more than one. However, we can decide finite number of solutions. Among all these solutions, we can measure the function value, and we can decide the maximum and minimum. That's the idea for the method of Lagrange multipliers. Let's go to problem. Okay. And for this one, we solved the problem earlier. Find the volume of the largest rectangular box in the first octant with three faces in the coordinate planes and one vertex on the plane using the method of Lagrange multipliers. Earlier, we tried to solve the problem in this way. The volume is x, y, z, and we have that, so that that can be rewritten in this way, x, y, and z can be written 6 minus 3x minus 2y, and 6 minus 3x minus 2y. And then from here, gradient of f, okay, in fact, gradient of v is 0, 0, and from this one, we try to x and y. That's what we did, and the computation is a little bit complicated. Now we'll try to use the method of Lagrange multipliers for this problem. The same way, the objective is v, that is x, y, z, and constraint is this one, so that is g of x, y, z. Now we have three variables, and if we try to use the method, then we'll introduce lambda. So there will be 4 unknowns. But here, the gradient of v, that is, x derivative will be yz, y derivative will be xz, z derivative will be xy. Right? That is same as lambda. Okay. And x derivative is 3, y derivative is 2, z derivative is 1. And in fact, this is same as lambda gradient of g. Right? Okay, we have to solve this problem. Now, if you look at this column, then from xyz, this one is missing x, missing y, missing z, so that you may try to multiply x for this first one and y and z. Okay, let's try to do that. Then you can see some pattern. We multiply x, then there is xyz equal, there's lambda, and there's a 3x. Okay. X is multiplied for the first one, for the second one y, then again there is xyz and lambda 2y. And for the last one, we multiply z, and that is xy z, that is z. So we have this first equation, second equation, third equation, and that is the final fourth equation. Now, left-hand side is all the same, xyz. So right side must be same if lambda is non-zero. But here, if lambda is 0, then at least one of xyz must be 0, and then volume is 0. That is not the solution. So that we may assume lambda is non-zero, then left hand side is all the same, so right side must be the same. So from the equations 1, 2, 3, we can get 3x equal 2y equal z. We can conclude this one. Now, by using the fourth equation, the constraint, and we already know this term 3x, that is here, 2y, z, these are all the same. 3 terms are added, but they are equal, and the sum is 6, which means each one is 2, right? So 3x equal 2y equal z must be 2. From here, x must be 2 over 3, and y must be 1, z must be 2, and so that volume, the corresponding maximum volume, is the product of these quantities, so that is 4 over 3, right? That's the final answer, okay? Okay. A topless rectangular box is made from 12 meters squared of cardboard. Find the dimensions of the box that maximizes the volume of the box. Okay. Let's try to visualize the box. Here, that. Okay, that is topless box, and this one is like that. If this is x, then y, and z, then the volume is xyz, and the surface area, total surface area must be 12. And here, xz, this side, front side, and another one back side. So twice of the front side, and yz is that right side, and we have a left side, so the twice of that. And bottom area is xy, but it is topless, so that we have 1 xy. The total area must be 12. So we have to maximize this function subject to that constraint. Okay, so we'll use the method of Lagrange multipliers. Gradient of v equal lambda gradient of g. Gradient of v as yz, x derivative makes yz, y derivative xz, z derivative xy, right? And lambda, now we try to get x derivative, that is 2z, x derivative plus y. Okay, now y derivative, and then we have 2z, it will be 0, and from here we have 2z and plus x. Now for z derivative, we have 2x and plus 2y from here and here. Okay. Now we'll try to use one more time the multiplication technique, try to make the left-hand side all the same. And so that for the first equation we multiply x, for the second one multiply y, and the last one we multiply z. Then left-hand side, that will be all the same, xyz, and lambda, we multiply x, so 2xz plus xy. For second one, we multiply y, 2yz, and xy. We multiply z, 2xz plus 2yz. Right? Okay, again, once lambda is 0, then 1 over xyz, at least 1 over xyz must be 0, which means no volume. So lambda cannot be 0. Now xyz is the same for every this equation 1, 2, 3, and of course the constraint is the fourth equation. Now so the left hand side the same, right side, these are the same. So this term should be same, which means x must be y. So from 1 and 2, equation 1 and 2, we can get 2xz must be same as 2yz, so that we have x equal y. Right? Now, again, we try to compare. Okay, now we have 2xz, so these two must be the same. So 1 and 3, out of 1 and 3, we can get these two are the same. So the xy must be 2yz. That means x must be 2z. Right? Okay. And we have this, and so that from this we can say x equal y equal 2z. We'll use this finding to get xyz. Now we have to use this fourth one. So far we didn't use that equation. Now it's time to use it. Okay? xy are both 2z. So from equation 4, okay, 2x. So 2 times x is 2z and times z plus y is also 2z. 2y, that is 2z, and we have z. And here x and y are both 2z, so there's 4z squared, which is 12. Each term is 4z squared. So left hand side is 12z squared, which is 12. That means that z is plus minus 1, but it cannot be negative. We are using xyz for the length of sides, so it must be 1. If z is 1, then xy must be 2, right? So that from this one, x equal y equal 2, right? So if we multiply x, y, z, then x, y, each one is 2 and z is 1, so that the maximum volume is 4. That's the final answer. Find the extreme values of f of xy as x squared plus 2y squared on the circle. That is the objective function. We want to find the maximum and minimum. Now, that is the constraint g of xy. With the method of Lagrange multipliers, we may start with gradient of f equals lambda times gradient of g. Okay, for this one, x derivative will be 2x, y derivative will be 4y equals lambda. X derivative is 2x, y derivative is 2y. Okay, we reach this one. Now we write here the detail. 2x is same as lambda 2x, and 4y is lambda 2y, and that is the equation of the constraint. So we have three questions involving three unknowns. We have to decide these quantities. Now from 1, there's 2x equals 2x lambda. If we move this on the other side, then equation 1 is now 2x is common and 1 minus lambda equals 0. So we have x is 0 over lambda is 1. We have that. If x equals 0, so we start with this one. Now x is 0, then from third equation, y squared must be 1, which means y is plus minus 1. So when x is 0, we have y value plus minus 1. The second choice is lambda equal 1. Then lambda is 1, and from second equation over there, and we have 4y equal 2y. The only solution for that one is y equals 0. Then y equals 0, then from the constraint equation, x must be plus minus 1. Right? Y equals 0, then x squared is 1, so x must be plus minus 1. So we found 4 points when x equals 0, y is plus minus 1. When y equals 0, x is plus minus 1. Okay, so let's try to visualize the points and try to find the function value. That is radius 1. Okay, let's try to draw that a bit better way. Okay. Yeah. Is it better? Looks like an alien. Okay. Yeah. Now that's 1. So once the x is 0, then it's a vertical axis, and y is plus minus 1. So this point and that point. Y equals 0, then this x-axis, and x is plus minus 1. Okay, that one. Of course, this is 1 and minus 1. We have 4 points. And from the method, we found these points, and we have to evaluate function value. And among them, the largest one will be the maximum, and smallest one will be the minimum. Okay. Once x is 1, y equals 0 for that one, and f value, f is defined in this way. X is 1, y equals 0, then here f must be 1. When x is minus 1, f has the same value. Now x is 0 and y is 1, then f must be 2. When y is minus 1, it will have the same value. F is 2. So along this circle, the minimum is 1 and maximum is 2. So that is the final answer for the problem. Okay. Find the extreme values of, now, same function f of xy on the disk. Rather than circle, we consider the circle and inside. Now, already from the previous problem, already we know that along the boundary, the values are already decided. Okay, so maximum, minimum are known. For that one, we already know that at this point f is 1. Again, here f is 1 from the previous problem. Here f is 2 and f is 2. We have to find the extreme values inside, not only the circle, but inside the circle. In order to do that, we may check the critical points. Okay, so gradient of f is, now x derivative is 2x and y derivative is 4y equals 0. Then we can get x is 0 and y is 0. So we have a single critical point over there, right? Now at the point x is 0, y equals 0, so f value must be 0. So among these extreme values, smallest one is 0, largest one is 2, so that minimum is 0 and maximum is 2. Okay. Now here we'll consider multiple constraint, and we in practice will consider only 2 of them, but in reality problems will be along with many constraints, sometimes thousands, sometimes millions, but we'll deal with here 2. The same idea will be used for many constraints. The problem is the maximization of f of x subject to g of x equals c and h of x is d. Now, if we try to use the method of Lagrange multipliers, then we observe this one. Once it has more than one constraint, then, for example, contour of f of x is given, for example, in this way, and here increasing, f is increasing toward that direction, so maximum is happening. But constraint may given in this way and possibly that way. So that is g equals c and that is h equal d. So the maximum x must be chosen so that the x should satisfy these 2 constraints simultaneously. So in this figure, only the possible solution happens at this point. Now, if you try to consider gradient, then the gradient of f is normal to the contour. So that is gradient direction. It's increasing direction. Now, if you consider gradient of h and gradient of g, then none of this is parallel to gradient of f. However, this gradient of f can be expressed as a linear combination of the gradients. So that is exactly this one. Gradient of f is now gradient of g and gradient of h and linear combination along with the lambda and mu. So we can express in this way. So for functions of 3 variables, we have 3 equations from this linear combination, and there are 2 more, so there are 5 equations. And also the number of unknowns must be 5, x, y, z, lambda, and mu. So we can solve the problem with a finite number of solutions. Okay, so just that is a linear combination of the gradients of constraints. Okay, let's see this problem. find the maximum value of the function f of x, y, z equals z. For simplicity, we chose the object function, very simple, z. On the curve of intersection of the cone and the plane. Of course, this can be written 2x squared plus 2y squared minus z squared. Okay. Now, by using the Lagrange multipliers, we can solve it. The gradient of f is 0, 0, 1. All z derivative have a non-zero result. 0, 0, 1 equals lambda. Now, function z, when g is given in this way, that can be written in this way. So that is, now, x derivative is 4x, y derivative is 4y, z derivative is minus 2z, plus mu times for this one. Now, x, y, z derivative, the gradient is 1, 1, 1. So from this one, 0 is now 4 lambda x plus mu. Now 0 is from second one, 4 lambda y plus mu. From the last one, 1 is minus 2 lambda z plus mu. These are three equations from the gradient, and this is the first constraint, and there is a second constraint. We have 5 equations. Now, we try to match the similarity. Okay, from 1 to, here again, we can easily see that lambda and mu cannot be 0. Then, here, we can easily see that 0, and this is the same. So that must be the same. 4 lambda, 4 lambda. The remainder part, xy, must be the same. From first two equations, we can conclude x is y. Now the first one, and once x is y, then now that is 4y squared or 4x squared. It's the same as z squared. So that by solving that, we can reach at this one, right? Okay, we already know x is y, and z is plus minus 2xy. Now, first case is z equal 2x. Then, here we are trying to use the fifth equation. Okay, and so far we used the, okay, along here, we use the first equation, second equation, and now that is fourth equation here. Now we'll try to use the fifth equation. X is y, and z is plus minus 2x, but we start with this case. And there must be x plus x is y, so it's x again. Now, z is 2x, so there is 2x equals 4. This one is changed in this way. Now, 4x is 4, so x is 1. Then it is the same as y, and z is 2. So we concluded this one. How about the other case? Z is minus 2x. Then, again, from fifth equation, x is y, as always must be true. So the fifth equation is the same as here, x, and y is the same as x, and z is same as minus 2x. Then that is 4, right side. The left-hand side is 0, so impossible. So from that case, we cannot get anything. So here, this is the solution. So the maximum value in f and when, okay, is simple function z, so that is true. That's the final answer. Okay. Okay, that's the end of the section. Thank you.